Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be talking about special situations in which it seems like the situations where the reaction wants to go to 100% before equilibrating. And so this is going to be an introduction to what I call, or what is called, IF and ICE, or ICE tables. So let's get into this. Okay, so what we've seen so far is situations where we have a large K value, a large equilibrium constant. So therefore, the equilibrium wants to shift towards products, but we have zero reactants. So the reaction is going to shift towards the reactants, but it heavily favors products. So you know that the change in X is going to be really small. Or you have the flip or reverse of that. You have a really small K value that favors reactants, right? But you have zero products. So that means that it's going to shift towards the products, but it's going to be a very small shift because in this case, the equilibrium favors the reactants, right? And we saw how you could neglect X in those situations. Well, what if you have a situation where the equilibrium or the reaction is going to shift towards the products, but the equilibrium heavily favors the products? In that case, you're going to get a large change in X, and so you won't be able to neglect X. In those sorts of situations, we're going to have to do a two-step problem. The first part is going to be a stoichiometric problem, like a limiting reagent problem. And then the second step is just your normal ICE table that you've done before. So let me explain. This is going to seem complicated at first, but I guarantee that once you get the hang of it, you're going to be able to fly through these problems pretty quickly. Okay, so what am I talking about? Let me go over this example here. So here we have our generic equation, and we're starting initially with 3 molar A. So we have our concentration of 3 molar with A, 2 molar of B. We have 0 concentration of C, and we have 0.5 molar of D, right? So in this situation, the first thing you want to do is to determine which direction is the equation going to shift. And right away, we see that C has 0 concentration. So you can't have something with 0 concentration at equilibrium. So because you have zeros of C, you know that it's going to shift towards the products. So it's got to shift this way in order to make more C so that we have some C at equilibrium. However, look at the K value for this reaction. It's 1 times 10 to the 15. That's a very, very large K, right? So remember, large K means that you're going to have lots of product and few reactants at equilibrium. So the equation or the reaction wants to go this way. It's very heavily favors the product side, but that's exactly the way it's going to shift. So I have way too much product, so this is going to shift in such a way that at the equilibrium, I'm going to have very tiny amount of this and a whole lot of this. So that means that the change, the X, is going to be very large. So therefore, it can't be negligible. Can't. So it can't be negligible. So our X is negligible assumption will not work like we normally do. However, we can set up this situation in such a way that we can use that X is negligible assumption. And the way we do that is we assume, hey, since this equilibrium constant is so large, right? It's large, and therefore we know it heavily favors the product side. why don't we just do a stoichiometric calculation, like a limiting reagent problem, such that we'll assume that everything reacts 100% this way to completion. It's going to react to completion this way, right? It really isn't, but we're going to assume that it does. And then we'll figure out what is left after it reacts to completion. And then we'll have to go back the other way in order to rebalance. So let me show you what I'm talking about. So the first part is going to be a stoichiometric part. This is the IF table, the initial and final part. Now, when you do your initial final table, your if table or your IF table, you have to get your substances in moles. You got to calculate the mole amounts. You can't do it with concentrations. So here I have 3 molar, 2 molar, 0.5 molar. I can't do the IF table with molarity. I have to get it to concentration. What am I talking about? Concentration is molarity. I can't use molarity or concentration. I have to convert it to moles. I got to use moles for the first table that I'm going to set up. So for simplicity's sake, I'm going to assume that I have 1 liter of substance. So that way, the molarity ends up being the same as the moles, because when you have 1 liter and molarity is the moles per liter, well, the molarity then is the same as the moles. However, if you have a problem where your volume of your solution is not 1 liter, then you have to calculate the moles using the molarity, okay, and the volume, right? So again, just you would say moles is equal to the molarity times the volume. So you'd have to do that calculation first. But since I'm going to assume that the container or the solution is 1 liter, so the volume is 1, so therefore multiplying by 1 just gives me the same number in moles. Okay, so enough talk, more action. Okay, so let's do our IF table, right? So in this case, let me do the IF table down here first. So then that means for A, I'm going to have 3 moles initially. For 2B, I'm going to have 2 moles initially. For 3C, I'm going to have 0 moles. And then for D, I'm going to have 0.5 moles to start with. Now, this is a stoichiometric problem. It's like a limiting reagent problem. So we're going to go all the way this way. We're going to assume that the reactants here react to completion. And you'll notice here that I have A and 2B. So these are going to react in a stoichiometric amount. So for every 1 mole of A that reacts, 2 moles of B, double the amount of B will react. So which one of these is going to run out first, right? So if I have 3 moles of A, right? Again, you can see why this is a limiting reagent problem. I got to see which one is going to run out first, right? So if I have 3 moles of A, if that completely reacts, I would require double the amount of B, which would be 6 moles. Do I have 6 moles? No, I have less than 6 moles. That means I'm going to run out of B first before I run out of A. So that means this is going to go to 0. So I'm going to lose 2 moles of B. So this is going to go to 0. So I do my subtraction, my stoichiometry. So I'm going to lose 2 moles of this. If I lose 2 moles of this, then using the stoichiometry of 2 to 1, I'm going to lose half that amount of the A. So 2 moles losing 2 moles of B means I'm going to lose 1 mole of A. I'm going to lose half that amount. So I'm going to lose 1 mole of A. And then again, using the fact, look, I'm going to lose 2 moles of this, right? There's a 2 to 3 ratio here, and there's a 1 to 3 ratio here. It'll be easier to use this one. I'm gonna lose 1 mole of this. Well, if I lose 1 mole of A, and there's a 1 to 3 ratio here, then I'm gonna gain 3 moles of C. So I'm gonna go and gain 3 moles of C. And again, since it's a 1-to-1 ratio between A and D, if I lose 1 mole of A, that means I will gain 1 mole of D. So now I've figured out what I'm going to lose and gain stoichiometrically, assuming that everything reacts and goes this way. So it's going to go 100% in this direction. It's going to react completely. So what do I end up with? That's what the F is for. So the F is the final mole amounts that I'm going to end up with, right? So then I subtract 1, so I'm going to end up with 2 moles left of A. I subtract 2 from 2. That means I end up with 0 moles of B, and then I'm going to end up with 3 moles of C, and I'm going to end up with 1.5 moles of D. So 1.5 moles of D. So now I have the moles at completion. So this is the first part. So I did my stoichiometry. I assumed, okay, given the fact that my K value is so large, let's assume that it goes to completion. We're going to do our stoichiometry. We're going to do a limiting reagent problem to see which one gets used up first. Now that I have what is left in terms of moles, now I can do the ICE table. Why? Because now I have the initial amounts that I need for my ICE table, and now look here. I have 0 in the reactants place, but the equilibrium favors the products. So now I can make the equation, or again, not make the equation, but now I notice that now the reaction is going to go in this direction in order to reach equilibrium. And because it's favoring the products, it's going to shift slightly this way. So now I have my ICE table, my equilibrium problem. So I do a stoichiometry problem first, figure out what my moles are, and now I can use that to go ahead and do the ICE table. Now, before I go to the ICE table, I cannot use moles. I have to convert this back to molarity, right? So since I am assuming 1 liter of substance, the moles that I have ends up being the same as the molarity. But again, in your problem, whatever the problem is, you have to take the moles and divide that by the volume of the solution that whatever the problem is giving you. So if it's 500 milliliters, then you're going to have to divide each of these by 0.5 liters to get the molarity or the concentration, right? So if I'm going to divide these by 1 liter, then I get the molarity. Now I can change this, right? So now at equilibrium, or at the initial concentration, it's going to be 2 molar here. I have 0 here. 3 divided by 1 is 3 molar. And then 1.5 moles divided by 1 liter is going to be 1.5 molar here. So now I have the initial concentrations after the reaction has gone to completion this way. But now, because I have 0 reactants, it's got to shift a little bit this way. And I can do the ice table that we've done before. And now I can do the X is negligible assumption. So let's go ahead and do that. So now I have ICE. Okay, so we don't need this anymore. It's served its purpose. And so now I can do my ice table. So I know it's going to shift this way. So again, using the stoichiometric amounts, I'm going to lose a certain amount here and here. So I'm going to lose an X amount here. So I'm going to lose X amount here because there's a 1. Is 3 there, so that means I'm going to lose a 3x amount here. Here I'm going to gain a 2x amount because there's the 2. And then I'm going to gain an x amount there because that's a 1. And now all I have to do is add these together to get my equilibrium concentration expressions in terms of x. So this is going to be 1.5 minus x. This is going to be 3 minus 3x. This is going to be 0 plus 2x is going to be just 2x. And then 2 plus x is obviously going to be 2 plus x. Okay, so now I have the equilibrium concentrations in terms of x. So now I can plug that into my equilibrium constant expression. So remember, the KEQ is equal to products over reactants. So 3C, so that's going to be the concentration of C raised to the power of 3, because the coefficient is a 3. And we're going to multiply that by the concentration of D to the 1 power, because the coefficient is 1. We don't write the 1s. They're there, though. It's understood to be a 1. Now we're going to put the reactants on the bottom. So we're going to divide by the concentration of A raised to the 1 power, and then multiplied by B, the concentration of B, raised to the power of 2. So there's our equilibrium expression for the KEQ. And so now we can plug in the equilibrium concentrations in terms of x. So let's go ahead and do that. So we're going to have C. So C is 3 minus 3x. Oops, I forgot that 3x. So 3 minus 3x multiplied by the, oh, that should be cubed. Sorry, I forgot the cube. So there's a cube there. Multiplied by the concentration of D, which is 1.5 minus x over, and then the concentration of A, which is 2 plus x. And then multiply that by the concentration of B, which is 2x, and that's going to be squared. And so now that we have our expression in terms of x, now we can go ahead and apply the assumption of x is negligible. Because again, since in this situation here, since k is large, it favors the products. So it's going to shift this way away from products. But because it favors the products so much, we expect that it's going to shift a little tiny bit, so that the shift or the change is going to be so small that it's not going to make a difference in the original concentrations. So here, when we're subtracting x, we can assume that that's going to be negligible, so we can get rid of x there. Here, 3x so small, it's going to be negligible, so we can get rid of it. And then here, again, we're adding x. X is going to be so small that adding a little bit of x is not really going to change the 2, so we can get rid of all of those. And so let's go ahead and get rid of these. So we'll get rid of that one, that one, that one. We're not going to get rid of that x because we're not subtracting x or adding x to anything, so we can't get rid of that. So now this will simplify to the following, which is going to be 3 cubed times 1.5 divided by 2, and then times 2x squared. And of course, this is equal to the equilibrium constant, which is this one. So that's going to be equal to 1 times 10 to the 15. So now all we need to do is solve for x. So this is going to be 3 cubed is 27. So what we can do is we can get x on both sides. So let's rewrite this. So over here, so we have 3 cubed times 1.5 divided by 2 times 2x squared, and that's going to be equal to 1 times 10 to the 15. So we can get x on this side, so we can get it on top. So if I multiply both sides by 2x squared, and then multiply this by 2x squared, so then this cancels out with this. So then this is going to be 3 cubed times 1.5 divided by 2. And then that's going to be equal to 1 times 10 to the 15 times 2x squared. So now we can calculate this, right? So 3 cubed is 27. Divide that by 2, multiply by 1.5. When we do that calculation, where's my calculator? Let's go ahead and do that calculation really quick. So 27 times 1.5 divided by 2 equals, maybe we get 20.25. So we get 20.25 is then equal to 1 times 10 to the 15. And then, of course, 2 squared is 4. And then x squared is x squared, so we can then bring that out. So we got 4 times x squared. And so now we can divide both sides by this. So if we divide by 1 times 10 to the 15, and also divide by 4, so we'll divide this side by 1 times 10 to the 15, and we'll also divide it by 4. So then this cancels out, and then we end up with x squared is equal to this, right? So let's rewrite it up here, 20.25 divided by 1 times 10 to the 15 divided by 4. So all we have to do is now calculate this, and when we calculate that, we get, let's see, 20.25 divided by 1 times 10 to the 15 divided by 4 equals, and we get 5.0625. So x squared is equal to 5. What did I get? 0.0625, 0.625, oops, 5.0625, so 5.0625 times 10 to the negative 15. Let me check my, yes. And now all I have to do now is, what's I'm looking for? Square root, yeah, square root, sorry. So I'm now going to take the square root, and then I get x is equal to, let me take the square root now. Where's the square root? Equals, and I get 7.1 times 10 to the negative 8. So 7.1 times 10 to the negative 8. So you can see that x is quite small. And this is what we would have expected. So we got our x value. And so now we can do the 5% calculation to determine whether the x is negligible assumption is valid. So let's go ahead and do that. And so here we would look at which one is going to give us the largest error. So here we have 1.5 and x. Here we have 3 and 3x, right? So these are both larger. And then we have 2 plus x. So if I was to pick one, it would look like that this one is the one where they are probably closest together. So you could do that one. And if you're ever in a situation where you can't really tell, it's hard to tell which one is going to give you the most error, you could just do all 3 of them and then see if any of them have an error that's 5% or greater. And now, I'm not going to go ahead and do the 5% rule because if you look at this number here, it's so much smaller than any of the concentrations that that it's going to definitely be less than 5%. But you can go ahead and calculate it and prove me wrong, but or prove me right. Either way. So in this case, then we can figure out what the concentrations are going to be. So since here, let me erase this. Give us some room. Okay, so then since we eliminated x from these 3, then the concentrations at equilibrium are going to be 1.5 for D, 3 for C, and 2 for A. And then for the concentration of B, it's just going to be 2 times x. So we take 2 times 7.1 times 10 to the negative 8. And that's going to give us, let's see, 1.42 times 10 to the negative 7. And so that would be the concentration of B. And let me just double check that. So we have 7.8. So yeah, so here's the concentration of B at equilibrium. Okay, and that, ladies and gentlemen, is how you attack these sorts of problems. So again, if you have, in this situation, we had a lot of product, and we had also zero reactant, or no, I'm sorry, we had zero product to begin with, but it was going to go in towards the product in a very large way because the equilibrium favors the product. But you could also have it in the other way, right? So you could have the K is very, very small, right? This could have been a negative 15. In such case, it would be very heavily favoring the reactants, and it would want to go this way a large amount. But what if you had zero reactant, right? So in the problem we did for this video, I had zero product, but it wants to shift largely in the product direction. That would be a situation where you want to do the stoichiometry first, assume it goes 100% in that direction, and then go backwards with the ICE table. So do your stoichiometry table with the initial final, the IF table, and then do your equilibrium table, the ICE table, right? But you could also have the situation where K is very small and therefore it's going to shift in this direction, and you could start off with a zero amount of one of your reactants. So in that case, the equilibrium would shift this way to create reactant, but that's the direction it does want to shift. It favors reactants. And so that would be another situation in which you would have to do the stoichiometry first, right? Make it go 100% in that direction or this direction. And then once you figure out what you're left with after the completion of the reaction, and then you could do your ICE table. But remember, again, let me state that when you do your stoichiometry, if you're given the concentrations, you got to convert that to moles first. Do the stoichiometry, do your limiting reagent reaction, and then when you figure out what mole amounts you have after the completion of that reaction going 100%, then you got to go back and recalculate the molarities of your substances, your products and reactants, and then do your ICE table using the new molarities, okay? So I hope this was helpful. Again, it seems overly complicated or quite complicated, but again, just keep working at it, and before you know it, you'll be able to do these sorts of problems really quickly. If you enjoyed this video, if this helped in any way, then please, by all means, like the video, share the video, hit that like button somewhere down here. Do me a favor. Join my channel, right? Subscribe. That's what I mean. Hit that notification bell up there after you subscribe, so that way you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem you need help with or a question, yeah, let me know. I'd be more than happy to help you with that. Thanks for joining me, and have a great day.